Okay, ladies and gentlemen, first thing we're going to talk about today, mole ratios in compounds. And the first compound we're going to talk about is a simple one. We're going to talk about H2O. Now, in the big scheme of the world, doing all our chemistry fun stuff that we're doing, we usually don't end up dealing a lot with individual elements. So we don't deal with those as much as we're going to be dealing with compounds. So we need to understand what this symbol gives us, the H2O, and how we can find everything from it. Now, the first thing that we're going to talk about in this first video that I'm making, because today I'm making a couple, this is about finding the ratios of each individual atoms in one, in this case, molecule, for example, of water. In water, you have an oxygen, and then you get a couple hydrogens that are tied to it. So there's an oxygen. So if you have one oxygen molecule, how many hydrogens do you have? Two. So there are two hydrogens, and how many oxygens are there? There's one. But if I put another one up there, that's a hydrogen, that's a hydrogen. Not drawn to scale, of course. Now I have two. So for two molecules of H2O, how many hydrogens do I have? Total. There's 4 hydrogens total. How many oxygens total? 2 oxygens total. Now, we can go on and on and on and put more and more molecules together until we have, let's say, 6.00 times 2 to the negative 20, or 2 to the 23rd, not negative 23rd, 2 to the 23rd molecules of water, which is what do we call 6.022 times 10 to the 23rd molecules? Well, yes, it's Avogadro's constant, which is awesome, but it's a 4-letter word. It starts with an M. A mole. So 1 mole of water has 6.022 times 10 to the 23rd molecules of water. 1 molecule of water has how many hydrogens? It has 2 hydrogens. And how many oxygens? 1 oxygen. So if 1 molecule has 2 hydrogens, 1 oxygen, if we put Avogadro's number, 1 mole of molecules together, then we got to ask ourselves, well, how many hydrogens are actually present if I have all these different molecules? If I have 6.022 times 10 to the 23rd molecules, each molecule has 2 hydrogens in it. So we're going to end up with 2 times that as far as the number of hydrogens in this. And that's where this actually comes into play really nicely. Because if I say, all right, if I have H2O, and if I have 1 mole of H2O, what I can say is I have 2 hydrogen moles, or 2 moles of hydrogen. That's even better. That's 2 moles of hydrogen atoms in 1 mole of water. Would you agree with that? The example that I've been using all day is when you bake a cake and you put 3 eggs in it, you only have one cake, right? But inside that one cake, there are 3 eggs. If you have 10 cakes, how many eggs do you have? You have 30 eggs. So there are a lot of eggs in 10 different cakes. Just like if there's 1 mole of H2O, there's a lot of hydrogens in there. There are a lot more hydrogens. There's actually 2 times as many hydrogens as there are molecules, because there's 2 in each one. And we get that ratio from the actual formula itself, the H2O. Now, how many moles of oxygen are there? Yeah, there's 1 mole of oxygen in 1 mole of H2O. And the neat thing is, when you build water, it's always built the same way. You build it 1 molecule at a time. So you have to build it with 2 hydrogens and 1 oxygen. You can't build it with 1 hydrogen and half an oxygen. If half oxygen, that means you have to cut the atom in half. And what happens when you destroy the atom? Big explosions happen, because a lot of energy is released. Yes?
So, basically, 2 hydrogens and 1 oxygen makes 1 mole of H2O?
2 moles of hydrogen and 1 mole of oxygen makes 1 mole of H2O. Now, there's another one that I really like, because it has a lot of stuff in it. It's dioxin. You don't want to ever play with dioxin. It's a poison. The chemical formula for that is C12, H4, Cl4, O2. So, dioxin, nasty stuff. We don't want to play with this. But, take a look at the ratios here. You have 12 carbons to 4 hydrogens to 4 chlorines to 2 oxygens. And if we're ever going to do any type of conversions or any type of things, and we're going to get into something called limiting reagents, where if you only have enough of one thing, like if I only have 5 hydrogens, I can only make 1 molecule. If I have 12 carbons, 5 hydrogens, 4 chlorines, and 2 oxygens, I can only make 1. And I'm going to have an extra hydrogen, because I need 4, 4, 2, and 12. It has to build like that. That's the formula for this. I can't build it any other different and get dioxin. So if I want to build dioxin, I need the 12 carbons, the 4 hydrogens, the 4 chlorines, and the 2 oxygens. Otherwise, it just doesn't happen. Now, from each of these, 12 moles of carbon in 1 mole of dioxin, 4 moles of hydrogen in 1 mole of dioxin. There's 4 moles of chlorine in 1 mole of dioxin. And there's 2 moles of oxygen in 1 mole of dioxin. So we've created 4 conversion factors if we needed to convert any other way. If I wanted to figure out what's the mass of carbon in 1 mole or in 1 particle of dioxin, I would have to use this. And I would have to use a bunch of other stuff. But this gets to the point where whatever we're dealing with the fact that we're going to have a chemical formula, and that formula tells us the recipe of what's going on. But it also tells us that there's 12 carbons in 1 dioxin. There's 4 hydrogens in 1 dioxin. And there are laws that state that dioxin has to form like this. The only time I can form another one is if I have 12, 4, 4, and 2 of those elements. The only way I can form another one is 12 carbons, 12 hydrogens, 4 chlorines, and 2 oxygens. I can't form it with 2 chlorines. It doesn't work.
So you said you could make it like H12?
I could, if I had 12 hydrogens, that means I could potentially make 3 dioxins. No, it's like saying if you have water, if you have 12 hydrogens and you're thinking about water, which is H2O. Well, how many molecules of H2O can I make here? I can make one that has 2. So now I have 10 hydrogens left. So can I make another one? Let's say I have enough oxygen to actually make it. So I can make another one. So now it's to 8. So can I make another one? Yeah, oxygen and 2 hydrogens. So that's to 6. Can I make another one? Oxygen to hydrogen. So that's to 4. Can I make another one? Yeah. Can I make another? And that's down to 2. So can I make another one? I can make one more. Because then I'm out of oxygen. Or not out of oxygen, out of hydrogen. So I can make one more. How many did I make? 1, 2, 3, 4, 5, 6. Yep. So you can take that 12 divided by 2, because I know I need 2 hydrogens. Divided by 2, I can make 6 potential ones. If I have enough oxygen, because now that tells me I can make 6 of these, I have one oxygen in each one, I need 6 oxygens in order to make it work. So it gets down to recipes. It gets down to, well, if I have 12 hydrogens, I divide that by 2 because I need 2 in each one. I can make potentially I can make 6 molecules of water. So I better have 6 atoms of oxygen in order to make it happen. Just like if I had 24 carbons up here, how many dioxins could I possibly make? If I had 24 carbons, I could make a potential of 2 of them, but I better have 8, 8, and 4. If I had 8, 8, and 4, I'm good to go. Does that make sense? Kind of, sort of? That's kind of like a preview of the reactions that we have that are coming up. But the idea that everything is built into ratios and that these ratios have to stay. The ratios are 100% locked into place. For dioxin, it has to be 12 to 4 to 4 to 2. For water, it has to be 2 to 1. Otherwise, it's not going to be water. It's not going to be dioxin. If it's sodium chloride, NaCl, what's the ratio? NaCl. How many sodiums do I have? 1. How many chlorines do I have? 1. So I better keep it in 1 to 1, because if I have 5 of these and 4 of these, how many can I make? I can make 4 total, because I need 1 to 1. If I had 5 sodiums and 4 chlorines, how many sodium chlorides can I make? 4 total. Is there going to be extra? Yeah. There's going to be 1 sodium extra. It's like if you had 11 eggs and the recipe called for 10 eggs, are you going to have an egg left over? Yeah. And when it comes down to that, for us, it's all kind of like recipes. Fish?